Orbital diagrams are a more pictorial way of expressing electron configurations. They give us slightly more information as well. In each orbital diagram, each box or horizontal line represents one orbital. Electrons are represented with half arrows, a half arrow pointing up representing the spin up electron, and a half arrow pointing down representing the spin down electron. Just like electron configurations, they are arranged in order of increasing energy. The lowest energy orbitals will be drawn on the bottom of the diagram, and the highest energy orbitals will be drawn on the top of the diagram. Sometimes to save space, they're drawn left to right. So lowest energy would be left and highest energy would be right. As you fill in orbital diagrams with electrons, you follow the Aufbau principle, filling in lower energy orbitals first before moving to higher energy orbitals. For example, the orbital diagram for helium has 2 electrons. They both go into the 1s orbital because it is lowest in energy. You would not put one electron in the 1s and one electron in the 2s because there is room for the second electron in the lower energy 1s orbital. We can continue looking at the orbital diagrams for the first 10 elements. Lithium has an electron configuration of 1s2, 2s1. The first 2 electrons go into the lower energy 1s orbital, and the last electron goes into the higher energy 2s orbital. Beryllium has an electron configuration of 1s2, 2s2. We fill in 2 electrons to each box, with one of the electrons pointing up and the other electron pointing down. Boron has 5 electrons, 2 of which are in the 1s, 2 of which are in the 2s, and 1 of which is in the 2p. By convention, we usually do the spin up electron first, and by convention, we usually do the leftmost box first, but it doesn't really matter. However, once we have an arrow pointing one way, the next arrow in the box must be pointing the other way. Otherwise, the electrons would not be following the Pauli exclusion principle. Once we get to carbon, we need one more rule to tell us what to do. Do we put the 6th electron in the same box as the 5th electron, or do we put it into a separate p orbital? Kuhn's rule tells us that for orbitals that have the same energy as each other, notice they're drawn side by side here, we need to maximize the number of unpaired electrons. In other words, for those degenerate orbitals, we need to maximize the number of electrons with the same spin. We can only have a second spin-up electron if it is in a different orbital compared to the first spin-up electron. I like to think of this rule as the roommate rule. Electrons do not like having roommates. They would rather live by themselves, so if the rent costs the same, they will take their own apartment. Kuhn's rule tells us the 6th electron in carbon is filled into the second 2p orbital. The 7th electron in nitrogen gets filled into the third 2p orbital. Once we get to oxygen, there are no more empty 2p orbitals, so we have to start pairing the electrons again. Oxygen has 1 pair in the 2p's. Fluorine has 2 pairs in the 2p's. Finally, neon has pairs in all of its orbitals from 1s through 2p. Remember, neon is a noble gas, so it is unreactive. The reason it is unreactive is that it has a full outer shell.